Now we discuss pumping lemma for testing regular languages, that is type 3 languages. And strangely, it is discovered in 1959-16, formally written. And strangely, because I'm saying 1936, Alan Turing wrote his paper, the Turing machine. It's much more advanced. And you will see 61, 62, the pumping lemma 2 for context-free languages come. So these are look very strange. Okay, what is pumping lemma is very simple. Like it basically comes from pigeonhole concept. Here you see there are 9 holes are there, pigeonholes. So if there are 10 pigeons, definitely at one particular hole there are definitely 2 pigeons. It is a very common sense problem. So using these common sense techniques, the pumping lemma says that if the language like this, you can make a breaking like string x and y and z, and you can make pump at y, that is at this level. So this is a test of regular language. If it is a necessary condition, not sufficient condition, we will see it later that Myhill Nerode theorem is more stricter, more necessary and sufficient condition, but that is difficult. It is a little bit difficult. So what's the pumping lemma? One says, say if you are producing infinite variety of strings from an input and with a finite state machine, there will be some state like here it may be repeated, and there may be another place there it may be repeated, but there is no synchronization to repetition. If there is a synchronization, that would attract the pumping lemma 2, like a to the power n, b to the power n languages. But here it can have a b to n c language, or a n b c language, or a to the power m b to the power m. There is no relation between m and n. We can prove it by the repeating state. So this is the Myhill notation. We can split any language like such a way x, y and z, and mod y, length of the thing must be 0, and pumping length, this p is for pumping length, is the integer. This integer you can take any integer. Necessary sub condition that the pattern should repeat like this. Next slide. I'm coming to same. This is here we can prove that 0 to the power n and 1 to the power n. 0 here is a string, 1 to the power n. It cannot be it cannot obey the pumping lemma 1, because you cannot, this string you can make a simple your x must be consist of 0 certain portion, and your like if you show the string here x must be consist of only 0, and your z must be consist of only 1s, and you have a y which should be a combination of 0 and 1. But if you repeat that 1 more than 1, then it is definitely not 0 to the power n, 1 to the power n. So mod of y would be 0. So that is not allowable in pumping lemma 1. You can see it should be mod y should be greater than 0. But here you see here x is only consists of 0 part, and z consists of only 1s, but you cannot find such a y so that you can pump. So it doesn't make a necessary test condition for pumping lemma 1, but it is for pumping lemma 2 we will find it. And same the pigeonhole principle, there must be 2 pigeons. If more than pigeonhole, if you want to allocate 1 pigeon 1 hole, if it is more than 1 pigeon, it should be accommodated, and 1 hole must be there are 2 pigeons. This is a pumping lemma 1, not only x, y, z. One might consider in some other textbook they may be represented by UVW. Same thing, U is here stands for x, and y stands for v, and this same concept, the v is being repeated, it's being pumping, rather we use the pumping term, and here instead of x it is u, and y it is here v, and z is here w. So but basic concept the same. We should know the different notations so our knowledge will be better, and this is a pigeonhole principles. This is pumping lemma 2. Here you see the little bit complexity. Here instead of we have 5 components u, v, x, y, z. I am taking from Michael Simpson. not only x, y, z, it is now uv comes here and v and y are linked together, and the pumping should be together, and v and y should be greater than 0. And now you can ask what is the difference between pumping lemma 1 and pumping lemma 2. Remember, in pumping lemma 1, 3 parts, x, y, z or u, v, w. Here it is 5 parts, u, v, x, y, z. So it is better to stick to convention x, y, z here, and here you must break it u, v, x, y, z. Pumping is only one place, y place, as per Myhill said, and 2 strings v and y, and constant x, y must be, but the pumping length should be greater than mod of x, y. Here pumping length like v, x, y, and non-empty. I've told that pumping, this middle, where the pumping is going on, it must be greater than. Here also it's greater than, and the basis is finite automata, and here context-free language's basis is parsing. Like this is a parsing tree. Here it is basically pumping lemma 2. This is pumping lemma 1, and this is pumping lemma 2. Here it is being pumped. Vxy, Vxy, it is being pumped. There is more better technique than pumping lemma 1, that is called Myhill Nerode theorem. It is very simple that there would be any language, whether it is a regular language or not, so you must compartmentalize, like at the strictly divide and conquer type of equivalent classes of languages consist of, and there will be no overlapping definitely, and infinite number of equivalent classes should not be there. That is means by Myhill Nerode theorem. We can use pumping lemma 2 for certainly not regular, but this one much more stricter, Myhill Nerode theorem. Here you can see in particular diagram, say there is 2 sets of language. It must end with 1. The C1 set of all language is ending in A, and C2 not ending in A. So we can make 2 divisions, C1 and C2, and we make such a diagram. So this is basically a regular language. So what is the difference between pumping lemma 1 and Myhill Nerode theorem? This is pumping lemma 1 for testing regular language. I told it is necessary condition, but not sufficient. But it is both. It is a finite that cannot be pumped, that's true, and count equivalent classes. It should be finite now. And equivalent classes, we know that 2 classes can be equivalent if we can merge the 2 classes. Basically, behavior of final state machine should not be changed. The necessary, this is sufficient, often easier to apply. So we use the pumping lemma only for easier cases. For it is not guaranteed that after obeying pumping lemma, it is in language is regular. Then we must use the Myhill Nerode. Thank you for